Hello friends, in today's class we are going to talk about a situation that lead to no progress called deadlock. Welcome here, and we are talking about the deadlock problem. What is a deadlock? And that I think we have already introduced in previous section what exactly is the deadlock situation. We have already seen a two process solution that may lead to a no progress, and that was deadlock. So and also in the Danning philosopher problem also we have seen that if we put the wait for chopstick I and each process execute this one, then wait for the next one, the wait for chopstick I plus 1 modulo n will lead to deadlock situation. So no progress, and infinitely people's processes are waiting for others to free the resource. Okay, processes are waiting other process or processes to free the resource. Okay, so that situation is basically deadlock, and here now we will formally understand this deadlock thing. Set of block processes holding a resource and waiting to acquire a resource held by another process in the set. Okay, so holding a resource and waiting for acquire another resource is called held by another process is lead to a situation that is deadlock. Example can be system has two tape drives, two processors require two tape drives, and P1 and P2 holding one tape drive and needs another one. Okay, so that is a situation where P1 is the process and it required two tape drives, and P2 is the process that required two tape drives. There is only two instances of the tape drive, and this is allocated to this one, this is allocated to this one. They are holding it and waiting for others to free. Suppose A and B is the semaphore that initialized to 1, then wait 1 will execute very successfully, and it will suppose at the same instance preemption, and wait B execute successfully. Then this wait B and wait A executed by P1 and P2 will lead into a deadlock situation. So to describe the deadlock or theoretically understand this, we will develop a system model. Okay, and this system model consists of what? It will consist of your resources. And remember that semaphore is also a resource. Okay, so because this is a way of synchronization, and we consider this as one of the resource. So here we have system consists of resources. A resource type is R1, R2 and Rm. CPU cycle, memory space, IO devices, all are resource. Each resource Ri had Wi instances. What is the meaning of it? That suppose there are two tape drive. Okay, so here in that case, if there is a two tape drive, then resource type is your tape drive, and there are two instances of it. Okay. Each process utilizes the resource as follows: request, use and release. Okay, so you request for the resource that you want to use the resource. First the request will come, then you'll use the resource, and then finally you are going to release it. If we if we characterize the deadlock, then we find that there are few things that that is bound to occur if the system is deadlock. And deadlock can arise if 4 conditions hold simultaneously. Okay, so this is the characterization of the deadlock, that if this 4 condition hold simultaneously, mutual exclusion, right? We want that the synchronization is having one of the requirement that the process should be executed in mutual exclusive manner, and only one process at a time can use the resource, right? So that is one requirement, and that is one of the key idea behind synchronization. Hold and wait. Process holding at least one resource and waiting others acquire additional resource held by the another process. Hold and wait, and just this is an example of hold and wait actually, that 2 tape drive, one is allocated to each one of this process, and they are looking for another process, another tape drive held by another process. So hold and wait. Okay, no preemption. A resource cannot be released can be released only voluntarily by the process holding it, and after that process has completed its task. Okay, so in between no one can come. Means if a process is holding, suppose, a tape drive, and so this tape drive cannot be abruptly taken away from this process. Okay, it is voluntarily, means when it is done using that tape drive, then only it is going to release the resource, and that is no preemption. And the last one is your circular wait, and the circular wait is a situation to describe here in this way, that P2 is looking for a resource of tape drive and P1 is looking for the resource tape drive. Okay, so P1 and P2 both are looking for a tape drive held by another process. P1 is looking for a tape drive held by P2, and P2 is looking for the tape drive held by P1. Definition wise, there exists P0, P1, Pn waiting for the process, such that P0 is waiting for the resource held by P1, P1 is waiting for the resource held by P2, Pn minus 1 is for Pn, and Pn is waiting for P0. So if you look at this graphically, then this will look like this: P0 waiting for P1, P1 is waiting for P2, P2 is waiting for Pn minus 1, and then we have a Pn, and Pn is waiting for something that is held by P0. Okay, so that is circular wait. So that is this condition will hold simultaneously, then only deadlock can arise. Mutex lock, mutual exclusion locks, the semaphores. Deadlock can occur via the system call or locking, etc. The dining philosopher problem is when we have the chopstick, as I said, I mentioned you, that is a semaphore, and that can also lead into this problem. Okay, I have referred it from some, okay, it's not important for you. This is from the Galvin book, so I've taken from the Galvin book as it is. Okay, examples, if you want, you can look at the page number 318. Okay, so that is your deadlock situation, and we have a few example, and here we have seen the characterization, definition held by another resource type, system model we have seen, and we have already characterized this deadlock, when deadlock can arise. Okay, so that's all for this discussion. Okay, in the next section we will talk about resource allocation graph. Thank you.